Hello and welcome to wasmCloud Weekly, the last one that we have for the month of January. And we've got some really nice updates for you. A lot of things we last week released RC6, found some stuff, fixed some stuff, and we're getting close to cutting an RC7. And RC7 is going to have some pretty cool other goodies that are going to be inside it. And I'd like Lucas to talk about what you built.
All right, so let me share my screen here. Okay, and the other side. Nice. So this week we are really focusing on observability and stabilizing the code base. We added many features between RC5 and RC6. With RC7, we are just addressing everything that is a bit of a leftover here and closing some open threads. So really focused on completion, not so much on adding more features here. And one of them is observability. So we had previously threaded tracing throughout most of the code base, but we didn't wire up OpenTelemetry to it. So all the traces were kind of happening, but there was no way to get that information out of Wash or from the host. So what we did here is we did that plumbing, and the pull request here that I have open is the one that we are introducing the OpenTelemetry setup. Key thing here is OpenTelemetry will be configured using the OpenTelemetry SDK environment variables, which is really well documented and allows you to configure every single little bit of how OpenTelemetry will interact with your application. And this is an important call out because this means you're not gonna have many flags inside wasmCloud that will be conflicting with the reporting that goes to your console output, like the logs that you get when you run wasmCloud, and also the traces and logs that are going to OpenTelemetry. This means they are total different feeds in wasmCloud v2. When you manipulate Rust log, the environment variable that most people use to debug Rust applications, you're dealing with the console output. So essentially the one that you get when you run wash. So if we do wash, let's do wash dev here. And here we can see the default info. If we go to debug, now we get way more output here. And this is how most people likely debug wash issues when they are looking at things locally. However, we have also to consider here the amount of data that it's being sent over to OpenTelemetry. So it would be kind of impossible to run a system that has this level of tracing enabled and have that running 24/7 in production. The same way, tying the flag that drives observability to a tag that handles debugging is sort of a problem that we're addressing here. In wasmCloud v1, the only way to enable tracing in wasmCloud was to actually do exactly this. You either set it to debug or to trace, and that's how you get tracing. Now, you don't need to set any of this. And tracing is going to be respecting whatever value you request here. So this way, if you want information in your console, you use Rust log. If you want to control what is going to OpenTelemetry, you use the log level here. So big setup, big kind of preamble here, but how does it look like? So we need to stand up here an OpenTelemetry receiver. So for that, we're going to use something called Aspire dashboard. And I'll essentially just copy and paste this here. Nice. So what this is giving us is a place that we can go and see logs, traces, metrics, and it opens up a port for us to do that. Now, while this thing is running, we're going to go back to Wash, and we're going to tell Wash that we now want to use OpenTelemetry. So what we're doing is essentially saying, go send OpenTelemetry spans over to this address here and use the gRPC protocol. And these environment variables here, they are documented in the OpenTelemetry documentation. So you can pretty much look at them and see the right values, what you can pass, what you cannot pass. Once we do this, we kind of ready to go. So let's start a wash dev. Do I have one close here? Yeah. So doing wash dev on Blobby. And the interesting thing here is the setup here is pretty easy to get going, as you can see, and gives you a pretty good idea of how observability is going to look like once you deploy in production, because the runtime is exactly the same. So traces, naming, all those things will remain stable. We are taking a quick look here at logs, and as you can see, logs, they kind of mirror what we're seeing on the terminal. The interesting thing about logs is that if there is a trace associated with that log, we are also linking it. So you can see a log message here and say, let me drill down on that thing. I'm not going to click on this one because I'll jump to traces as a list here now. Another interesting thing with logs is that you don't get just this message here. You get some more context. So you can pretty much filter on these things on your observability system. Now for traces, the interesting thing here is that this is giving us a pretty good overview of all the steps that Wash is taking throughout its execution. So the very first thing that happens when you run wash dev is we're going to call all hooks that are of type before dev, because we are about to do dev. Right after we do that, we do a component build. And interestingly, the component build also calls some hooks because we are building. So before and after, we also call some hooks. After that, we load the component into the runtime. And this one is an interesting one because it starts to give us a pretty good idea of where our time is being spent. And because it is a bit of a more nested trace. So you can see here that we spend a lot of time just parsing the component itself. And after we parse the component, everything else is pretty quick. As we are bringing up the workload, we might also have to bind external plugins to it. And here we have an example of two plugins binding to this workload. We see here Blobstore, and this is going to be the same for Blobstore. And the next one is for WASI logging. This is because the component that we just loaded here uses WASI logging and Blobstore. And at the very end, we link all the components, and at this point, the component is up and ready to receive requests. Now, up until this point, we haven't interacted with the component at all. We simply loaded it up. What happens when we actually exercise the component? So let's go to Blobby and just reload here. All right, so now we have two extra traces here. This is because we have one HTTP request for this page and one HTTP request for the list of files inside Blobstore. The very first one, which is the basic one, just getting the HTML, we can see here that even though it's just returning HTML, the Blobby is doing some extra calls into Blobstore, which is kind of an interesting find. Why is it doing that? But regardless, we start to see here that when we handle the HTTP request, we are extracting also the proper host, method, and the path that this request is coming in. And as we learn more information about this request, we also continue to enrich the trace here. So on the first span, we know the host. On the second span, we now know exactly which workload ID, name, and namespace this request is being routed to. And this allows you to essentially gather this information and create dashboards and observability targets that can compose these traces and the information that are in these traces. If you want to create alerts for a specific team when something is going slow, you can put an alert on a namespace, my team name, and every time there's a trace with this shape here that is taking more than 1 second, you alert. So that kind of logic can be constructed here. The other interesting part is this part here is being executed. Everything that we're seeing here is being executed by the runtime in Rust. Now, there is a hop happening here into WebAssembly and back that is important to call out. We received HTTP request in Rust. We invoke the component, and this is WebAssembly. Within that call, the component is using Blobstore to do a get container, and container exists. And even though this is going to WebAssembly and coming back, we still keep the trace here aligned and things within the correct context. So we can go here to this container exists and will tell us that, yeah, somebody used this container here, this component, used Blobstore, and they were trying to get the container blobby. So all this information now that is happening inside plugins and is happening inside the runtime is easily traceable with this pattern that we have here. And as you can imagine, logs, they are also there. We have some stuff happening, but they don't carry as much rich information as the traces that we have. We have not added any metrics up on this point, but we have most of the instrumentation already in place. Is another situation where it's a matter of plumbing to OpenTelemetry and start emitting. But we feel like with this level of information here, we're pretty good. We're in a pretty good spot to know when things are happening inside the runtime, inside a component, when they're being executed by plugins and so on. And we also made sure to not enforce any observability requirements on plugin authors. So as somebody developing a plugin, you don't need to sprinkle instrumentation code throughout your plugin. Most of the binding operations, unbinding operations are instrumented from the outside, from the engine. So it becomes pretty easy to create new plugins and get instrumentation right out of the box there. So cool stuff here. I'll take a quick pause, see if there's any comments in chat. And Bailey, not sure if you want to add something else here too.
Yeah, you probably saw I just unmuted. I think it's also worth highlighting. So you made it where you don't have extra work on these plugin authors because a lot of this already is happening automatically by what you've added to the host. Did you have to add any OTel instrumentation to Blobby to make any of this work?
No, so Blobby is the same Blobby as before. The interesting thing here is because Blobby uses Blobstore, and Blobstore is a wasmCloud plugin. We have the instrumentation in the wasmCloud plugin, and we take care of the context on our side.
So if I'm using basically any WASI API that's already supported by the host, I drop in my component, and it's basically auto-instrumented for me.
Essentially, yes, pretty much.
Pretty cool. Pretty cool. I see we have a question from Frank.
Yeah, this one. So does this work as you're showing in a kube environment?
Good question. It does. And I'll try to bring up the cube environment here quick because it also shows how I bring up the cube environment locally, and a lot of people might laugh at that. All right, so I took down wash. I'm keeping aspire up. From here, I'm going to open another terminal, and I'm going to bring up nats. Then another terminal, and we bring up the operator. This one will take a while. It shouldn't. And while that's coming up, good. Now we bring up the host. So I should have a host that I ran here before. Yeah, there you go. So bringing up a host, HTTP address, host group, and all of those things. Now, as this is coming up, we should go back here and there you go. We just saw connections to NATs. And notice the difference here. So as we just booted up the host is already doing things in the back, sending the workload start operations, getting workload status, and it's sending the workload start here because I'm pretty sure I already had some workloads deployed here. Yeah, exactly. I was testing Blobby before, which means I can do this. Yes, and we just exercised that, and we can take a look now at the traces that it emitted. So here we're connected to NATs. We received a workload start, and you can see exactly what's going on during the workload start, which is kind of mind-blowing. You notice that during the workload start for the host case, most of our time is actually spent here pulling the component from OCI. So all that time that looked significant in Wash development regarding parsing the component is actually not the culprit here anymore. We spent 1.8 seconds getting the component from OCI. And then we went on to bind the plugins and everything. So you can see that most of the trace here from workload start downwards looks the same. But because we are running in Kubernetes, we have this extra layer here, which is the NATS API doing this. And similarly for workload status, same thing. Also important to say that the information about what workload ID are we requesting status about, we are also passing that. Similarly for workload start, we also know exactly the workload here, although it should be nice to not have this sum here. Gonna remove that. But yeah, and you can see here the path is exactly the same. For the component request traces, exact same thing. And as you can imagine, the host name here is going to be the namespace default, workload name, the Kubernetes name, and so on. Does that answer your question, Frank?
Yeah, it does. It looks really great. The question in terms of loading the OCI image, is this a locally starting, I mean, you cache this or are you still retrieving from a registry?
This
And
one
I'm
is
just
retrieved.
wondering,
There you go. And which is amazing because this is kind of one of the questions you would have when you're looking at this trace is, what is this coming from? So we know that we're pulling a component here from this OCI image.
so in theory, if you have all those images cached, they'll be much faster.
You got it. Yes. Awesome. If no other questions here, I'll give it back to you, baby.
Yeah, thank you, Lucas. That's awesome. I actually really enjoyed seeing you how you test locally. That is actually really great to have on video. I might refer back to it later. Okay.
I was thinking the same thing.
Yeah,
Yeah, it's always
actually,
helpful.
I use the video in order to do installation. So, because the documentation is outdated. So I
Yeah,
use,
so that's not on Eric. I will say that is 100% on me. Eric got the PR up, but we hadn't merged it because Eric's updates showed me that we had some bugs, and I was like, no! And I didn't want to dock the bugs, you know? Like I didn't want to confuse people by making an update and then like ch changing it again. So went fixed the bugs, and they'll be fixed in RC7, and that's when we'll rep the docs again. Sorry about that. Anybody else have questions? If not, I want to do a special kind of doc of the week, which is a blog post that Eric worked on with a whole lot of people. It's basically the oral history of the past, you know, like how did WebAssembly come to be and what have we done over the last 10 years? And it's a really wonderful read. Eric, you did such a good job. Um, if you haven't read it and you don't know this history, please go and read it. I gave a talk from what happened in my perspective with all of this, but so if you want to hear, you know, my reaction to like how incredible this was in 2012 when I first saw it. You can do that, or you can read these tidbits where people were like, okay, so we just told each other, told each of our managers that they're on board, even though they maybe might not have necessarily said that they were on board, but so long as they could keep that coalition together to get this thing out the door, we're gonna make WebAssembly happen across all of these otherwise competing browser vendors. So it's a really cool story. And yeah, we've posted it in lots of socials, so if you're on one of those, you can probably find our post and repost and boost it. We just put it out this morning. So yeah. Anybody anybody have questions for Eric about this one? I had a lot, but I've already gotten to ask them. All right. Well, geez, thank you, Eric. I really appreciated you creating this. If it really somebody in the pull request for it actually said, you know, this is going to be one of those articles that people refer to years from now, and I'm like, yeah, 100% will be. I can't wait to see the 20 years of WASM post that points back to this one, and just talks about how we changed everything. Yeah, I should have already posted that, and I didn't. My bad. Here we
it
go.
probably would be interesting to see um, the, I mean, what is the acceptance curve? Because I mean, it would be great to see after we're over the hump, and it looks like we're still in the what? This is not really being adopted in general, right? I mean, there's some pockets there, and it'd be nice to see what's the evolution of this if
Yeah.
we have that kind of information.
Well, we do have the telemetry to say that it's used in billions of devices today. If you are using basically a modern TV, watching Disney Plus, if you're using CDNs, or if you're on the Zoom blurring this background right now, you're using WebAssembly. So in terms of as a technology being adopted, it couldn't be more ubiquitous than it is right now in terms of web environments, where you're talking about the adoption curve is very much on the server side of WASM, where are we going to turn this curve? And a lot of that really comes from the web gives you an operating system that's sandboxed, and we've been building out basically our own equivalent of that with WASI. There's just a lot more to add, and folks are really expecting to be able to lift and shift, but they didn't have that exact same expectation for moving to the web. And I think that's part of why that curve has been slow. However, what I'm expecting to happen in about, let's give it 2 months. In about 2 months, I'm really expecting a massive adoption shift when we actually have threads in WebAssembly, which is one of the biggest things that has been a pain point for people to lift and shift. It's a pain point both for the code that they write, where they have existing code that uses something like threads. It's also a pain point on languages. So a lot of folks, the reason why it's kind of slow to adopt is that a lot of people for a long time had to use effectively statically typed languages like C, C++, Rust. They had amazing support for WebAssembly, but we mere mortals often weren't able to write in those languages. We were a lot more comfortable in things like Go and TypeScript and scripting languages. And as those get better support, and specifically with the cooperative threads feature inside the component model that allows languages like Python to have a really nice native compilation experience, we're going to have so much more adoption. That's been the big holdback, I think.
Yeah. So one thing I think probably would be interesting is right now we're stuck with languages because this is where how you bridge the gap between, let's say, requirements and something that you could run. But with all the automation with LLMs, right, all over the place, I think that it becomes, requirements to Rust, and that's it. So I think that it probably be interesting to have a thread in terms of, okay, how you take existing problems and not wait for Java to be there, but just what is the function that you're trying to do, and then have your tools put something together in terms of Rust. I think this will be probably an interesting thread.
Yeah, it's actually something that I'm seeing play out with a lot of the folks that I'm talking to. Basically, anybody that's in a large enterprise that's experimenting right now with WebAssembly, they've all come to the same kind of conclusion, which is, wow, LLMs are really, really good at writing Rust code. And it makes sense. The compiler tells you what you did wrong. It's very explicit about what to fix and how to fix it. You've got structured types, and so when you're trying to solve a problem and you're doing it with an LLM and Rust, yeah, you can do it very efficiently. And so a lot of people, I have actually seen a lot of people do a conversion from something that was in Python to Rust so that they could have something working in WebAssembly quickly. I really do expect that to be a major trend this year. We'll see more of that. It's hard though to expect enterprises to do a conversion like that. You know, if somebody wrote C++ code 20 years ago, the thought of changing it is kind of scary. And so I also get the folks that want to stay where they are and not do a massive conversion. But if they're in C++, hey, they can drop in and build with WASI SDK easy peasy right now.
Actually, in our environment, they're really pushing for people to use more and more automation on code development.
And automation specifically using code gen from LLMs.
Yes.
Yeah, interesting. I love it.
Actually,
It's really cool to hear other people's perspectives. I'm seeing it everywhere. Yeah, so I mean, this year might also be the big unlock because folks now, it's not the mere mortals can write Rust very easy because they've got tools to do it. And that means that they get access to this really great ecosystem in WebAssembly. From there, I think the next big unlock would very much be about, getting things like request and Tokyo and all of these common dependencies that people already depend on, having those have a WebAssembly target natively supported. In a language like Rust, where we actually do have a formal target for WebAssembly, you don't have to add some special kind of SDK on top to make it work. And an example of that actually is I'm actively deprecating our once supported SDK called Cargo Component inside the Bytecode Alliance because you don't need it anymore. You just say WASI, WASM32, WASI P2. You don't need a special adapter. Rust just supports WASI P2 as a compilation target straight out. So you don't need that extra adapter step. You don't need these extra tools to kind of cobble the thing together as a stopgap. Now the standard language library just supports what you need. The next step is getting all of these different sort of ecosystem libraries to also have WASI P2 as a supported target, and eventually WASI P3. And those just come down and compile easy peasy as well. What a lot of folks need to see for those foundational libraries is stability. And I'm hoping that with some of the presentations that we're building over the next month, where we're going to be talking about our road to 1.0, which is post WASI P3, that we're not going to create a P4, for example, that we are on the road to 1.0 now, which means road to stability. I think we can get more confidence by a lot of the folks that have to maintain things that we're not going to churn a lot on them and we're not going to break their end users. And so they should feel a little bit braver about merging some of these PRs that bring in something that has the word preview in it.
Yeah, just to mention one more thing on the Rust side. I mean, they can even evaluate. I mean, how stable, how good the crates are. So
Or
you
you
don't have
think,
to.
like from a crates.io perspective
Yeah,
or some
yeah.
other trick? Yeah.
Uh-huh.
That's a fun discussion topic. It's obviously near and dear to me. It's basically like, how do you make the world a better place by making people write secure software that can be sandboxed? I think it's one of the most important missions that we can actually just make the software that we're using every day better just by making it compatible with WebAssembly and, not have double after free. It's pretty exciting. Well, anybody else have other stuff, other topics they want to talk about? PRs they want to get in, anything like that? Otherwise, we're through all of our agenda items for today. All right. Well,
I wanted
hey.
to ask something. Sorry.
Hi, Aditya.
So what happened with the wasmCloud crate, and why does it point to uh, wasmtime-wasi also points to our own internal implementation? I think that was with regards to the TCP UDP lookup, because I'm facing a lot of issues with my pull request for the gRPC outbound handler. And so I was just wondering, yeah, could we just talk a bit about that?
Yeah. I'll say a few things and then hopefully Lucas can fill in the rest that I don't cover. But essentially, we have one crate that we forked from wasmtime and we've brought it inside Wash, largely because we are dramatically enhancing what it does with TCP loopback. And that's so that we can implement our service feature inside Wash. So now you can have a component connect via TCP loopback with our service. And so it's kind of like virtualized networking without having to drop all the way down to the network stack. Should be extremely efficient, and we can do a lot of different things on top of that that we can expand. And the reason why it needed to be in like the WASI socket implementation is obviously the component is saying, I want to talk to WASI socket. And then we virtualize that binding with our service that we're hosting in our host. And the concept of a service is wasmCloud specific. It's not something that wasmtime can know about. And really, again, a lot of that exists because there's a lot in the component model that hasn't yet been realized, like runtime instantiation. But we're bringing all that power inside the wasmCloud host today and building it out ourselves. And then as the standard evolves, we'll obviously adapt to it. So with our service that is more long-lived, has a different lifetime from our individual components, we've got to do something a little bit different and special. So it is a problem though, and and you can see my chunker of a PR to update to wasmtime 41, and I even created an upgrade guide so it's kind of clear. One of the challenges that this wasmtime-wasi crate is sort of a large thing that has both the file system, clocks, and sockets, and I only really want to edit sockets. So I think in an ideal world, we would be able to upstream, breaking up this into something that's more modular. So having a crate, the only piece that I actually want to either with hooks or by breaking apart the crate so that I could just patch in a crate that is just for WASI sockets. That would get me a lot further along than having to do a fork, but we wanted to get this feature in as soon as possible because we're driving as fast as we can to release our V2 MVP. So that's a little bit of that background. and why it exists. And you can check out the upgrade guide that's now on main to see exactly like what's the difference between these two and how we do an update. Lucas, is there anything you would add
Thank you
there?
so much. Yeah, I'll just take a look at the upgrade guide because I'm quite confused because there's a lot of conflicting dependencies. Like there's two dependencies pointing in the two different wasmtime-wasi. So yeah, thank you so much for clarifying. And yeah, I'll take a look at it.
Awesome. Yeah, I just want to mention here, like it's an interesting situation because we need like a 10, 20 lines change in the WASI crate. But to get that 10, 20 line changes inside the WASI crate, we need to align with a lot of people, have many conversations, think how this will be addressed in Windows, Mac, Linux, and so on. So the scope is a bit large, and we really wanted to move fast here. So the change itself is tiny, but all the dependencies that change is bringing, that's what hurts, and it hurts a lot. It really feels here, kind of giving a parallel, early days of Linux when you start getting everybody on the same kernel, but then Red Hat comes along and has their kind of custom version of the kernel. And a lot of people were expecting Red Hat to upstream those changes so everybody could have the benefits and everybody be on the same kernel. That's kind of what's going on here. Because we are trying to move fast, the amount of communication and alignment that is required to get this in the main line is significant, so we forked. But in forking, we created also all these headaches for ourselves in terms of dependency. You try to bring in wasmtime HTTP, and suddenly it doesn't work because it relies on the WASI crate, which is now a different crate. So that kind of problem, we're really aware, and we don't like the situation, but this is really temporary. That's kind of how we're seeing it.
Thank you, Lucas. Yeah, makes sense. We need to iterate fast. Yeah. Thank you.
I feel your pain. So like TLDR though, refer to our crate in your changes. So the wash wasm time, but you know, in most cases the types are identical and never changed, and so it's compatible with the wasmtime-wasi crate. So cool thing about Rust is it'll let you know if it doesn't match and doesn't work, and you know, you iterate from there. But I can totally see why it's confusing, and yeah, I hope we can fix it ASAP.
All right. Thank you.
That's a good question. Yeah,
Lucas,
Jeremy?
you had a question inside the chat just on can you run this as a K8s controller?
Oh, if the service itself is a Kubernetes controller, it should work. And this would be an interesting one because as long as you can do TCP towards the Kubernetes API server, yeah, it should work. So first thing I will try is just have a simple HTTP GET with the vanilla HTTP client just to see how you get there. And the other important thing here is after you test with the HTTP client, don't use the HTTP client for the Kubernetes integration because I'm assuming here you want to use the existing Kubernetes libraries and you have to do HTTP using WASI sockets and not by a WASI HTTP outgoing handler. If you try to go WASI HTTP outgoing handler, you're going to have to change a lot in Kubernetes machinery. So this is to say that I think you can run a Kubernetes controller as a workload service. I think you would have bigger challenges trying to run it as a component inside a workload. But as a service, it might work.
Let us know if you get it working, because that would be pretty cool. Anybody else? It's been a good discussion today. All right, well, let's get back to merging these things. Hope you have a good WASM day.